Okay, this is section 7.7 called Products and Quotients of Rational Expressions. And this one is brought to you from Lowell High School at 5:45 in the morning. I couldn't sleep last night, so I'm up early making videos. So let's see how this one goes. This is my first video in the morning. Okay, products and quotients of rational expressions. When we're talking products, what we mean is multiplication, and by quotients we mean divisions. Or actually, let's put the division sign. For you folks that don't know, this sign right here is called, well, this is an X. I hope you guys know that one. This one is called an obelus. Obelus. Cool. So products and quotients of rational expressions. Pretty much what we're dealing with is multiplying fractions and dividing fractions. So when we multiply fractions, we can just multiply straight across. So a over b times c over d, we can just turn this into ac over bd. If I was to do this with real numbers, say 2 over x times 7 over 4, this equals 14 over 4x. Of course, we could simplify this by dividing by 2, which would be 7 over 2x. That's what we mean by products of rational expressions. When we talk about quotients, we're talking about divisions, and there's a special rule we have for divisions. When we're presented like this, what we do is we take this last fraction and we flip it. So this becomes a over b, and we change the division to multiplication times d over c. And this makes us able to just do our rule from before, so this will end up equaling a over b times d over c, just like that. Again, if we're using real numbers, let's say 1 over 2 divided by 3 over 7. This division is nasty. We don't want to try and think of that. That's saying take 3/7 and divide 3/7 into 1/2 as many times as you can. So what we're going to do is we're going to change it to 1/2 times 7/3, which ends up being, if you guys can see it, ends up being 7/6. Okay, so those are the rules that we're doing, and we're pretty much taking everything that we've done from the previous section and we're going to combine it all together. So let's do our first example. We have x squared plus 7x plus 12 over 12 times 4 over x plus 4. When we're looking at this, before you guys do the operation, factor anything you can factor every time. So this factors into x plus 4 over x plus 3 over 12 times 4 over x plus 4. At this point, since we have an x plus 4 up in the numerator and an x plus 4 down in the denominator, we can cancel these out. So now we're just looking at the multiplication of x plus 3 over 12 times 4, which is way easier to look at than dealing with the binomials. We could simplify this. We could take out the 4, and this would become a 3. And we end up with our answer of x plus 3 over 3. And we were able to get this answer without doing any multiplication. We did nothing but canceling out stuff we knew. So again, factor and cancel. Okay, that's going to be the name of the game for this. Let's do another example. Here's x squared minus 64 over x squared minus 16 divided by our obelus, x plus 8 and x plus 4. The first thing I'm going to do is factor. If you notice here, we have different squares. We actually have it twice. So we can change this into x plus 8 times x minus 8 over x plus 4 times x minus 4. Instead of doing division, I'm going to flip this fraction and do multiplication. So this becomes x plus 4 over x plus 8. If I look here, I'm in a spot where I can cancel. So there goes the x plus 4s. Here goes my x plus 8. And I'm left with x minus 8 over x minus 4. Again, this is another one we didn't have to do any multiplication. Now, granted, my steps don't have to be followed exactly. You could have done the multiplication and then done all of this division or the canceling out too. That would have been fine also. It just tends to work better if you try and factor and cancel as much as you can at first. One more example. This is called a complex fraction. I don't know why it's called a complex fraction. It's just a fraction inside of a fraction. Why we need to call that complex, I don't know. We just do. There's a trick to get rid of these. And what we want to do is we want to find out what denominator has the highest degree. And it's this guy right here. So we're going to multiply by x squared to get rid of this. So we're going to do x squared times the top. And we're going to do x squared times the bottom. The reason we're allowed to do this is because x squared divided by x squared is just 1. So we're multiplying by a fancy version of 1, which is okay. We can multiply by 1s as many times as we want. Okay, so when we multiply this in, we got to remember it goes to both pieces inside of the parentheses. So it goes here and then there. So 12 times x squared is 12x squared. X squared times 6 over x. One of the x's will cancel, so this is left with plus 6x. On the bottom, we'll get 12x squared. And then when we multiply to the 3 over x squared, the x squareds will cancel, so we'll get rid of that, like so. Once we're here, we need to start to look for simplifications. So what can we pull out of the top? We can pull out a 3. Which will give us 4 plus 2x. And on the bottom, we can pull out a 3. Oh. We can pull out a 3x actually on top. There we go. That's almost looking better. Okay, that's looking more accurate. I did that too fast. This is what it should look like. I pulled out a 3x. If I multiply that back in, I would have 12x squared plus 6x. On the bottom, I can pull out a 3 and only a 3. So this becomes 4x squared plus 1. From here, I can cancel out a 3. So I'm left with x times 4x plus 2 all over 4x squared plus 1. So there really wasn't anything too complex about that. We're going to keep working on these for the next day. If you have any questions or comments, please let me know, and we'll talk to you tomorrow.